Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 19. We are in lecture 7, and we are starting a new section called Simple Regression. This is part 1. So in this section, we're going to introduce and review what we've already learned about least squares regression from last semester. Then we're going to talk about simple linear regression, derive the least squares estimators, define residuals and fitted values, talk about and derive the MLE and the estimators for the mean of y given x and for the variance. And then we'll talk about the properties of least squared estimators, both the expectation and their variance. So let's get started. So the objectives for this section are, when we're done, you should be able to use simple linear regression models to estimate unknown values. You should understand the steps to the proofs, the derivations, and be able to apply this knowledge to new problems. You should understand the assumptions under which linear regression is valid, and you should be able to derive maximum likelihood estimators for linear regression. So recall that a regression line is a straight line. For simple linear regression, it's a straight line that describes how a response variable depends on some explanatory variable x. So we can have a scatter plot where we have x and we have y, and the actual points, depending upon the strength of the association. Let's make this a little stronger. A little stronger association. So get some of the... Okay, so with that, the linear regression line is the line that goes through these points, the best fit line through these points, and it's not easy to draw by hand, especially for me. So this is the regression line. And it models the data or the points that are actually measured, because the points that are actually taken from the sample will create a cloud, a scatter plot, and depending on how strong the correlation is, that determines how much spread there is from the line. And we measure the spread in the vertical distance. So this point would be further away than this point. So we measure in the vertical distance, and the higher the correlation, the better or the more variation that's explained by the regression line. Okay, because there's less of it, and so we have, as correlation increases to -1 or to +1, or as it decreases to -1. In other words, as the absolute value of r approaches 1, the correlation is stronger. And if we have r equals 1 or r equals -1, then we have a perfect correlation. Okay? And then all points are on the line. So regression line can be used to predict, say, the heart rate, which is y, of a patient who receives a specified dose of a new drug, the dollar amount, y, of collision damage to a vehicle from impact speed, x, on the vehicle. Another example is timber volume, y, of a tree from a diameter x, the strength y of a concrete specimen from the amount of a certain additive. So we can do these predictions of y based on x, assuming that we have a statistically significant correlation. And that's a very important point. Okay? If you have a weak correlation and it's not statistically significant, you don't want to use it for prediction. Likewise, you may have a statistically significant prediction because that is based on sample size. So for a large sample size, it allows that R is lower, and yet you still have a statistically significant correlation. However, if the if R is around 0.3 and it's statistically significant, you still wouldn't want to use that for prediction because there's so much variation in the data that your prediction would not be very precise. Okay? So we've talked about this in sections 4.2 and 4.3 of last semester, and we showed that the linear association between two variables, x and y, is calculated using the correlation coefficient. This is the population correlation coefficient. This is also called Pearson's correlation coefficient, and it is the covariance between x and y divided by the standard deviation of x times the standard deviation of y. We also proved that rho was between -1 and +1, and this is an important property to know. And R, the sample correlation coefficient, is always between -1 and +1. We also showed that when rho, the absolute value of rho is 1, in other words, rho is -1 or rho is +1, then there exists these numbers, alpha and beta, such that the probability of alpha plus beta x is equal to 1. In other words, there's this linear association between x and y, and this linear formula for x and its support is alpha plus beta x. Okay? So when rho is equal to 1, then beta is positive, and when rho is equal to -1, beta is negative. Okay? And we derived the equation for beta, and there's two expressions for it that are equal, they're equivalent, they're identical, they're just different ways of making the calculation. All you have to do is substitute in the value of rho here from up here, and then the cancellation, and you'll get the second formulation. And we showed that alpha is equal to the mean of y minus beta times the mean of x. Now again, this is when rho is equal to 1 and rho is equal to -1. This exists. So that's one way to approach this. But we're going to approach it differently. Then in section 4.3, which was conditional distributions, we also showed that the expected value of y given x is equal to some value is alpha plus beta of little x, again for x in the support of x. And then we showed that the sum, the expected value, is for a discrete variable, is the y times the distribution of y given x in this case, which turns out to be written in this form, okay, is equal to alpha plus beta x again. So we have the expected value is equal to alpha plus beta, oh well, we have that right here, don't we? We have the expected value is equal to alpha plus beta x, and we have the mean of y given x, and that also is equal to alpha plus beta x. And don't forget your support, okay, whatever that is. When we solve for alpha and beta in terms of mu x, mu y, sigma x squared, sigma y squared, and rho, we get this equation for alpha, okay, which can be rewritten as the same equation before, mu y minus beta mu x. Now, what's important about this is we're getting the same equation, but we're coming at this from a very different perspective. We're coming at this from the conditional distribution instead of just purely the correlation. So here we address this problem using correlation equals 1. Here we're taking the expectation of y given x, and then the mean of y given x, the conditional mean. And these two are equivalent. Okay? And we're getting the exact same equations. Here's the equation for beta, which gives us another formulation here. And like I said, this agrees with our derivation from section 4.2. Now, in this new section, we're going to reuse the results from section 4.3 to define a simple regression model. Okay? And what we see is that this regression model exists not just when rho is equal to 1 or -1. That tells us how good the relationship is, but we can still use this model for the data. It's just, is it statistically significant? And then if it is it still, does it still explain enough variation for us to practically use it? Okay. So our notation that we need, y is the dependent variable or the response variable. There's many different names for this depending on which field of application you're using. That determines which notation is the most common. Okay, so certain fields, education, psychology, medicine, health science, they each have their own preference for the terminology they use for this. So x is our explanatory variable, or the independent variable, or the predictor is another name for it. So it's possibly useful for predicting y. Mu of y given x, so the conditional mean of y at the value of x, is given by this symbol here. And then the pair of points x sub I, y sub I, these are independent pairs of observations for I equals 1 to n being our sample size. So we first talk about the population regression line, and the population of paired x and y values are assumed to be scattered about a straight line, which is called the population regression line. And we use the formula from section 4.3. Mu of y given x is equal to alpha plus beta at beta of x at x. X being the random variable, little x being the actual value that we plug in for it. Okay, and so we have this line, and this is showing a positive slope, but it doesn't have to positive slope. But we could have a negative slope as well. So that would be a negative slope. In other words, as x increases, y decreases in this picture. As x increases this way, y increases. That's a positive slope. All right. So here are our model assumptions. And the model assumptions are things that we sometimes have to check, because if they're not true in our situation, then this model does not apply. And as statisticians, this is something that we have to know is very important. So the random variables y1, y2, up to yn, they are first independent of each other. So you could say that they are at least pairwise independent. You might even be able to say they're mutually independent, but usually we talk about pairwise independence. They have normal distributions. This is a big assumption, so has to be checked. This we can verify graphically, and we'll use residual plots to do so. They have to have a common variance. Have to check. We'll perform a test for equality of variances. Have means. Mu sub I equals E of y given x equals x sub I, and that is equal to alpha plus beta x sub I. So this is a mean. We're talking about the line here is a mean line through the points. So that's how we can think about this line. Is that it's a average through these points. And we'll find out that that is quite true. And it's always true that y is equal to mu of y given x plus epsilon, where epsilon is the random error. And this is another assumption based off of these assumptions up here, that the random error is normally distributed. That is from the normal distribution here. And that the variance is sigma squared, this is saying that we have a common variance. And then this is just what we expect from error. Error being a random error, then if the true value is here in the model, then all the deviations of the values around it, and then we would want this just to be on the y. Whoops, I still have too much. Okay, so let's say that we have points along the same y, pretend those are on a line, then as we have this variation around here, we expect that the average of that variation is at the average. Okay, so the average variation would be 0 as far as deviation from the point, because this is talking about error or deviation from the actual. Okay, random error, and we can define it as y minus the actual point, y. So if we take just one point here, and we have a line, and we choose x, little x, and this point here is mu of y given little x, the actual value, and here is a y value, an observed y value, then the error is this distance between the mean and the y, okay? And it's the random error. Now, y and epsilon differ only by a constant, which is that mu of y given x. It follows that y and epsilon both have the same variance, that the variance of epsilon is equal to the variance of y, which is equal to sigma squared. And the expected value of y is equal to the mean of y given x. And that's true if and only if the expected value of s is 0. And I'm trying to think, that's definitely a error. That's not supposed to be s, that's supposed to be epsilon. Okay, so this is true if and only if the expected value of epsilon is equal to 0. Y has a normal distribution if and only if epsilon has a normal distribution. So this is true because if y is equal to mu of y given x plus epsilon, the expected value of y is equal to the expected value of mu of y given x plus epsilon, okay? And this is equal to the expected value of mu of y given x, not x given x, plus the expected value of epsilon, and we know that this is 0, and this gives us mu of y given x. So this is just a constant, okay? And epsilon has a normal distribution. Then a normal something that has a random variable plus a constant it still has the distribution of a normal distribution, but now the expected value has changed to mu of y given x. And so if epsilon, this is the only random component of this equation, so if it has a normal distribution, this has no distribution, it's just a mean, a constant. So it doesn't change the distribution at all, it just shifts it. Then y is also a normal distribution, okay? Has to be. If this is just a constant and this is normally distributed, adding a constant to a normal distribution doesn't change the distribution, it just shifts the mean of the distribution, and so y is still normally distributed. And likewise, if y has a normal distribution, then we could take epsilon, again, is equal to mu of y given x minus, y minus mu of y given x. We subtract mu from both sides. So if y is normally distributed, I subtract a a constant, then it's still normally distributed, and that's what the error is. So that's why we're saying that the normal distribution of, if y has a normal distribution, epsilon has a normal distribution. If epsilon has a normal distribution, then it goes backwards. Then y has to have a normal distribution. And that's how we have this if and only if, or implies and is implied by. That's another way of stating that double arrow there. So we have an equivalent form of the model. Y sub I equals alpha plus beta xi plus epsilon I. And again, so this is a pure value. We set or determine x sub I. We control. We control or substitute a fixed value for x sub I. Okay, so we can set that value as long as it's in the range of the data that we have. We can plug it into this equation and actually calculate y sub I. Okay? And these are parameters. Alpha is an unknown parameter, beta is another unknown parameter. So they are population constants or population parameters. And again, we're saying epsilon sub I is normally distributed with a mean of 0, a variance of sigma squared. The epsilons are IID, so identical and independently distributed, okay, with a normal distribution, mean 0, variance sigma squared. This is a good place to stop. So we will stop this video here and pick up there in the next video. So if you have questions, please come to virtual office hours. If you need help before office hours, then by all means email me. I'll get back to you as soon as it's possible. Please take care of yourself because we want to see you next time.